All right, let's dive right into this explainer. Today, we're going to completely demystify a really fascinating piece of C code. It's a program designed to take human-readable math and translate it into a format that a computer can actually understand and process without breaking a sweat. So if you've ever found yourself wondering how a basic calculator or even a compiler actually interprets the equations you type in, well, you're in the exact right place. We are going to break down this Infix to Postfix converter, part by part, looking at the logic, the code, and how clever memory management makes the whole thing tick.
To really wrap our heads around this code, we'll navigate through our Translators toolkit in 6 distinct parts. We'll start with translating math for computers, then look at the stack array, push and pop logic, operator precedence rules, the translation engine, and finally, the main control room. Okay, part 1, translating math for computers and why we actually need a translator in the first place. So why do we even need to translate math? Well, the core problem is that you and I, we naturally write math as infix expressions. That simply means the operator, like a plus sign, sits right smack in the middle of the operands, like A plus B. But for computers, dealing with infix is an absolute nightmare. Think about the strict order of operations or the nested parentheses. To evaluate all that, a computer would have to constantly scan back and forth over and over again. Instead, computers vastly prefer a postfix structure. In postfix, the operands come first, followed by the operator, so AB+. It might look a little weird to us, but it allows the computer to process the whole equation in a single, super efficient left-to-right sweep, absolutely zero parentheses needed. And our C program's entire job is to pull off this exact conversion reliably.
Moving right along to part 2, the stack array, and setting up the memory for our translator.
Looking at the foundation of our source code, we see standard C libraries being imported to handle our inputs, outputs, characters, and strings. But the really important part, the thing you should absolutely take away from this, is the macro definition, max, set to 100, and the initialization of a global character array called stack. We are essentially carving out a neat, vertical column of 100 empty slots right in the computer's memory. This array, it's going to act as a temporary holding area for our math operators, your pluses, minuses, multiplies, while the program figures out exactly where they need to drop into the final output.
Now, to manage that memory, the code introduces an integer variable named top, and it initializes it right off the bat to -1. You might be wondering why -1? Well, remember that in C, array indexing always starts at 0. So if top was 0, the program would think there's already an item sitting in that very first slot of our stack. By starting at -1, we perfectly represent a completely empty stack. It's exactly like a physical stack of plates in a cafeteria. That variable top is our trusted pointer, telling us precisely where the highest plate currently sits.
All right, part 3, push and pop logic. Let's look at adding and removing items from that stack.
Now that our memory is all set up, the program needs to interact with it, and it uses 2 tightly controlled functions to do that. First up is the push function. When the program needs to save an operator to our stack, it follows 2 logical steps. Step 1 acts like a security guard, checking if our 100-slot limit has been reached. If the stack is full, it stops right there, preventing a nasty stack overflow error that would literally crash the entire program. If we do have room, we hit step 2, where we increment the top index and add the item. Notice that in the code, the 2 plus signs come before the word top. That's a pre-increment. It tells the computer, hey, first move our pointer up 1 empty slot, and then place the new character into it. Pretty slick, right?
Conversely, the pop function does the exact opposite. When it's time to take an operator off the stack and drop it into our final equation, pop steps in. Step 1 is our security guard again, checking if the stack is totally empty. If it is, it returns a null character so the program doesn't accidentally pull out garbage data from memory. But if there is an item, it returns the stack item and then decrements the index. Because the minus signs come after top this time, it grabs the item sitting at the current position and then lowers the pointer down by 1. It's just a beautifully simple and elegant way to manage data flowing in and out.
That brings us to part 4, operator precedence rules, where we rank the math symbols.
So, we have a stack to hold operators, but how does the computer actually know when to put them on the stack and when to pop them off? Well, it needs a rulebook. That's our precedence function. What's really fascinating here is how the code uses a switch statement to map mathematical symbols to hard numerical rankings. To translate math correctly, the computer absolutely has to respect the order of operations. So an exponent, represented by that little caret symbol, gets the highest value, a 3. Multiplication and division? They get a 2. Addition and subtraction get a 1. By assigning these strict values, the program can just compare 2 operators using simple greater than or less than logic.
If it looks at a multiply and an add, it instantly knows the 2 beats the 1, which dictates exactly how they flow in and out of the stack.
Next up is Part 5, the translation engine, where we set up the conversion function.
This Infix to Postfix function is really the central hub. It's the core translation engine where all those tools we just talked about finally get put to work. Inside this function, the code gathers its ingredients. It takes in 2 arrays, the original Infix array holding the user's math problem, and the empty Postfix array just waiting to be filled. It also sets up 2 tracking variables, I and j, starting at 0. I reads through the user's input character by character, and j is used to write the translated characters into the final output. Lastly, it creates a symbol variable, just a temporary little bucket to hold whichever single character we happen to be looking at during the current pass.
And finally, Part 6, the main control room. Let's bring it all together.
The main function is where the program actually starts running and where the user gets to interact with our toolkit. Before asking the user for a single thing, the program makes sure it has the physical space it needs. It defines the infix and postfix character arrays. Remember that max macro from the beginning? This officially reserves 2 distinct 100-character arrays in memory. Basically, one acts as the before snapshot, and the other is the after snapshot for our equation.
The final piece of the puzzle perfectly captures the entire user journey. It prompts the user to type in their standard math equation. Then it grabs that input and stores it safely in our infix array. Behind the scenes, it passes those arrays right into our translation engine. Once the engine does its hidden magic, the program spits out the brand new computer-friendly format stored in the postfix array. It's a completely seamless loop of input, process, and output.
But here is where things get really interesting. If you were to look closely at the full source code we've been breaking down today, you'd notice something missing. The actual internal loop inside the translation engine was intentionally left completely blank. We've been handed the architecture, but the actual plumbing is left for us to figure out. So, since you now understand the mechanics of the stack, the strict rules of operator precedence, and how the memory arrays talk to each other, I'm going to leave you with this final challenge. Using the exact tools we just walked through, how would you finish writing that character-by-character translation logic? Think about it, sketch it out, and until next time, keep exploring the code.